In geometry, we are going to look at exploring solids, cross sections, and nets. Let's start out with some vocabulary. So first, a polyhedron. So this is a polyhedron. Is a three-dimensional solid that is bounded by polygons called faces. That enclose a single region of space. An edge of a polyhedron is a line segment formed by the intersection of two faces. A vertex of a polyhedron is a point where three or more edges meet. The plural of polyhedron is polyhedra or polyhedrons. So then here's an example. We see that the face, this is a face, vertex, where they all meet, edge, the line segment. So a face are all flat surfaces of the solid. The edge is a line segment where the faces intersect. And a vertex is a point where three or more edges intersect. So then if we look at this one over here, we see this is a face. This is the edge, and this is a vertex. So we're going to classify solids. What makes a polyhedra? So these are all examples of polyhedra: a cube, a tetrahedron, dodecahedron, icosahedron. Not polyhedra. Here we have a sphere, a cone, and a cylinder. So if they have curved surfaces, they are not polyhedra. To name a prism or a pyramid, use the shape of the base. So a triangular pyramid, this is our base, right here. We see it's a triangle. A pentagonal prism has two bases, one on top, one on bottom. So those are the bases. And they are pentagons. That's why it's called a pentagonal prism. The two bases of a prism are congruent polygons in parallel planes. So my bases will always be parallel to each other. They will never touch one another. So we're going to practice tell whether the solid is a polyhedron. If it is, we're going to find the number of faces, vertices, and edges. So number one, yes, this is a polyhedron. This is called a rectangular prism. So then we're going to list number of faces, edges, and vertices. So faces, we see we have 1, 2, 3, 4, 5, 6 faces. So we have the top and bottom, front and back, left and right. Edges, okay, let's count them. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So 12 edges. Again, the ones that we can't see, we still count. And then vertices, where they all meet. 1, 2, 3, 4, 5, 6, 7, 8. Number 2, this is not a polyhedron because it's curved. This is a cylinder. Number 3, yes, it is. Look at the shape of its base. It has 1, 2, 3, 4, 5, 6 sides. So this is a hexagonal pyramid. So we'll do the faces, the edges, and the vertices. So the faces, we have 6 triangles that make up around the pyramid, and then we have the hexagonal base, so that makes 7 faces. Edges, again, we can count them. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12, so 12 edges. Vertices where they all meet, we have 6 down here on the bottom, and then the one at the top, 7 vertices. Number 4, this is not a polyhedron, again, because it's curved. This one is a cone. Number 5, yes, this is referred to as a triangular prism, because it has 2 bases, these triangles, which are parallel to one another. So there's one base, here's our second base. So we're going to do faces, edges, and vertices. So our faces, we have 1, 2, 3, 4, and then backside 5. So we have 5 faces. Edges, so 1, 2, 3, 4, 5, 6, 7, 8, and 9. And vertices, 1, 2, 3, 4, 5, 6 vertices. We have what's called Euler's theorem. This tells us that the number of faces, F, vertices, V, and edges, E, of a polyhedron are related by the formula. Faces plus vertices equals edges plus 2. We're going to use that to find the number of edges on the frame of this house. Okay? So we're going to start out with the faces and vertices. So faces, okay, I have front, back, so there's 2. I have this side, we're at 4. My roof, 5, the other side, 6, and then we have the foundation, 7. So we have 7 faces, which again are 4 walls, 2 roof, and 1 foundation. Now we're going to find the vertices where they all connect. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So now we're going to use this formula to find the number of edges, so we don't have to count all of those. So 7 plus 10 equals E plus 2. Solve this for E, so I have 17 equals E plus 2, so subtract 2. That tells me that there are 15 edges. Now we're going to talk about what's called a regular polyhedra. A polyhedra is regular if, number 1, all of its faces are congruent regular polygons. Number 2, the same number of faces meet at each vertex. There are only 5 regular polyhedrons. These special polyhedrons are called the Platonic solids. They are named after the Greek philosopher Plato, who wrote about them. So the first one, a tetrahedron, has 4 faces. 1, 2, 3, and then 4 and 5. One behind this one, one behind this one. Sorry, 4 faces. 1, 2, 3, and then the one behind this. A hexahedron has 6 faces. So front, back, top, bottom, left, right. Octahedron says 8, so it has 8 faces. We have 1, 2, 3, 4 triangles on the top and 4 on the bottom, which gives us 8. The last 2, we have a dodecahedron, which dodeca, remember, is 12, so it has 12 faces. An icosahedron has 20 faces. There are only 5 regular polyhedral because the sum of the measures of the angles that meet at a vertex of a convex polyhedron must be less than 360 degrees. Therefore, the only possible combinations of regular polygons at a vertex that will form a polyhedron are 3, 4, or 5 triangles, 3 squares, and 3 pentagons. The polyhedron is convex if any 2 points on its surface can be connected by a segment that lies entirely inside or on the polyhedron. If the segment goes outside the polyhedron, then the polyhedron is concave. So just like when we were doing convex and concave polygons, same type of thing. So it says find the number of faces, vertices, and edges of a regular octahedron. Octahedron, we already know that has 8 faces. We can find our edges. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So we say we have 12 edges. Vertices, we have 1, 2, 3, 4, 5, and 6 vertices. We can check ourselves using Euler's formula. So we're going to check using faces plus vertices equals edges plus 2. So we said there are 8 faces plus 6 vertices. Does that equal 12 edges plus 2? 8 plus 6, 14 equals 14. We did that correct. So now we're going to talk about exploring these solids. First, we want to talk about what a cross-section is. So a cross-section is the intersection of a plane and the solid. The cross-section can be different shapes, including polygons and circles. To draw a cross-section, you will visualize a plane intersecting one face at a time in parallel segments. Draw the parallel segments, then join their endpoints and shade the cross-section. So I have some examples for that. So here it says, what is the shape of the cross-section? So we see that we have a pyramid. This is our plane. We took it parallel, and this in here is our little cross-section. So what is our cross-section there? The shape is a triangle. On this one, we have a cube. The cross-section we see is a square. Again, we have a parallel cross-section. So now B, if we do our plane and at the diagonal of our cube, we see this is our cross-section now. So now we would have a rectangle. If we kind of rotate it and take that plane from corner to corner, so back corner to front corner, this is our cross-section. This is a trapezoid. If we take our plane and just cut off the little edge to get a cross-section, oh, I didn't shade that in very well. Again, you can see we have a triangle. I take a cone parallel to the base. I get my circle. If I take a hexagonal cylinder or prism, we see, again, we're going parallel. Again, we see that we've got that hexagon in there, so we would get a hexagon. Imagine if you cut some of the edges of that polyhedron and unfold it. The two-dimensional representation of the faces is called a net. And so here we have our 3D cube. If we were to unfold that, this is what the net would look like. Here's some more nets of common solids that we talk about. Rectangular prism, if we were to unfold that, this is what we would look at. A net of a pyramid, of a square pyramid. So we have the square on the bottom and then the triangles that come out. Net of a cylinder, we have the 2 circles on the top, and then this is going to wrap all the way around that rectangle. Net of a cone, so we have the circle, and then we have this shape. Okay? When we wrap it around, it creates that cone. In class, we're going to go to this website, GeoBra, and I'm going to put that up on the smartboard, and we're going to investigate some more of these cross sections and the nets, but you are more than welcome to go there on your own and investigate those, and where you can manipulate it on the computer and see that for yourself. So this takes care of our very first day, getting to know solids, cross sections, and net.